Okay. Okay, guys, welcome to the 12th lecture of Physics 140. And let me see where we were. A slight review. We were looking at photo emission as a way to give an explanation to the process. And we found that a good reasonable explanation for it, or a model to describe photo emission, actually requires to understand or to think about light as being a particle. And as I say here, it's a particle with let me see if I can scribble here. Okay. So it's a particle with no mass, as it says there. Let me see if I can. Okay, I can lock it down there. With energy and momentum, and when the particles are absorbed, they are absorbed by the electrons in a material. So this is what happens. Oops, I don't think I like this. Okay. Okay. So this is the particle, the electron, that absorbs all the energy provided by the photon. And in the next picture, the photon is gone. So it disappears, and all the energy that the photon is carrying in the backpack is given to the electron that carries away the kinetic energy equals to h nu. Okay, so whatever energy this particle had, it provides all the energy to the electron. So when a quantum of light, which is a photon, is absorbed from the many photons in the electromagnetic radiation, what happens is when it is absorbed by an electron, the electron obtains all the energy delivered by the particle. In generally, it's very rare that you can actually excite the particle twice, meaning once you have given him an energy by a photon and it's moving away, you then catch it up in the air and give it another one. That doesn't happen, you know. Essentially what happens for modest intensity electromagnetic beams is that a single photon is captured by one electron, okay? And that is good enough to actually explain the photoelectric effect, okay? So how can I get rid of this without... Can I carry it away? No, and if I stop it, I cannot draw. Okay, let's not draw it anymore. So a related process that is actually linked to the fact that the model that we have used to describe the photons is what I've just told you, meaning you can produce particles of light, is good to explain the production of X-rays by a beam of electrons. Okay, so the mechanism is the one that is depicted at the bottom left corner of the view graph. Here you have essentially you have a vacuum tube, which is this. Oh God, I have to do this again. Yeah, the vacuum tube is this thing there. That's the vacuum tube, and then you have a filament. This is a filament, the one on top here. This is a power supply connected to the filament. So when I heat it up, electrons will come out of the material by thermionic emission. Okay, so there will be a cloud of electrons free from the metal around here. And then I put a high voltage power supply as this one, with the polarity such that the electrons will feel attracted to the anode. This is the anode here in terms, the anode, yeah, and the rays are produced by the cathode or the filament. Okay, so this is where the electrons come out, and they are accelerated towards the anode, and then the electrons are fully deaccelerated in the collision with the anode material, and radiation comes out. That is the description of the phenomenon. Okay, so you have a beam of electrons collide with the material, and the electrons apparently deliver a large fraction of its energy to the photon field. Okay, in the right part of the view graph here, we have a better model of how the thing, the drawing is, it's better like this. This is usually a material that you can serve as a good heat conductor, because when electrons collide with the anode, there's a lot of heat dissipated, and you can actually melt the material if you're not careful enough, or the current is too high, or the voltage is too high. Still here, you need to put the power supply, and the power supply goes like this. So meaning positive in this side, as it shows here. And this piece is actually all the X-ray equipment usually have a water supply that is providing cooling water to this side of the instrument in order to keep this cold enough so it doesn't melt here. Okay. This material is, as in this case, is tungsten. Why tungsten? Because tungsten melts at a higher temperature than copper. That's why you don't use copper there, because it will melt very easily. So you put tungsten, but you use the good conduction of heat of copper to remove the heat from the tungsten so it doesn't melt anyway. And essentially, you do the same thing here. The electrons are accelerated towards the anode, and then when the deceleration is complete, X-rays come out. Okay, so the idea is that here on the right side is the resulting values of what we get for the intensity in the vertical axis as a function of the wavelength of the photons. Okay, you have to be reminded, yeah, that this is what is true here, that the energy of the photons are inversely proportional to the wavelength. So when I have a wavelength here, this wavelength, this is the highest energy in all the graph that I have here, because it's the lowest wavelength. Okay, if one compares with this equation here, and then this voltage here is the high voltage that you put here. Okay, we are changing that voltage from 20 kilo electron volt to 50 kilo electron volts. Okay, and did I okay, this voltage or this voltage here. Okay, those are the voltages that we are changing here as a function, and measure the intensity in each time as a function of the wavelength. So essentially, we do the following thing. We connect 50 kilo electron volts to this tube. We have it in operation, and we start measuring the intensity as a function of wavelength, and we plot it. This is the graph that we're seeing here. The intensity in the case of light means number of photons that we are actually shooting out from the tube. Okay, the larger number of photons, the higher the dose the patient will receive. Okay, so the question is simply one very, very interesting one, that the intensity seems to scale with I'm sorry. One thing is the intensity is scaling with the voltage here, which is okay. There's a different explanation for that, because this all, if I if I put a higher current, this is just done to display it better, but if I put a higher current on the filament, I will have a higher intensity. So I could actually do this experiment all with the same maximum intensity, but they will have something that I cannot modify. And what I cannot modify is the highest, the lowest wavelength of each one of the graphs, okay? Remember that the lowest wavelength means the highest energy. And what is the highest energy that I can give to a photon? The highest energy that I can give is the highest energy that I have available. And what is the highest energy that I have available? It is simply, the expression that I have here. It is essentially the voltage that I'm putting in, okay? I didn't write this up. Wow, that's bad. Let's write it up. Okay. So what is the expression? The expression is H nu max. The maximum frequency is equal to E times the applied voltage, okay? And this is nu max for each graph. This is nu max here, this is nu max here. So the maximum energy photon that is coming out of a 30 kilo electron volt has almost 40 picometers of wavelength, okay? Okay, here we go. So that is the relevant part. So if you make a graph of how this point here changes with the energy, you'll find a linear plot. In what sense is linear? It's linear in the frequency, in the maximum frequency. If you want to write it as a wavelength, you have to replace this expression here is equal to that over there, which is hc divided by lambda, okay? Remember that the Einstein model, what the Einstein model produced was this value here. This is what we learned from Einstein, and I'm using the same tool and the conservation of energy to actually describe what is the minimum wavelength of a certain radiation generated by the X-rays, okay? This is very, very, very small radiation. This is well, I calculate here this is what I did for 30 kilo electron volt. I actually calculated that it's 400 picometers, which is exactly the value displaying the graph here. So what I'm saying is, if I use an energy of 30 kilovolts, which is, no, it doesn't work that way. When I use 30 kilovolts there, this is a 30 kilovolts. So when I have 30 kilovolts apply, I'm using 30 kilo electron volts, because the energy of an electron volt is simply the energy, the charge of an electron multiplied by the difference of potential, and that's what gives the units of electron volts, okay? Now, so let me change gears a bit. This is one aspect. We have seen then the photoelectric effect is good to describe this this particle nature of the photons. I get a good explanation of how I could understand how the photoelectric effect works if I describe the light, the incident light, as particles. I have a similar good explanation for the highest frequency I could measure in the emission of X-rays by assuming that the X-rays are constituted by photons. And now I want to see how does the dispersion of the X-rays work, okay? Let me see if I could, no, there's nothing I could do here. Yeah. Oh, yes, I can. Perfect. Okay, so what I would like to describe now is the Compton effect experiment. Again, we have a source of X-rays there. So we have the high voltage applied to the tube. The electrons come and hit the metallic piece, and then radiation comes out. There's a collimating slit here. The materials arrive to the target, and what one can see is that this is the experimental result, that the light that comes out of the sample have different frequencies, and the frequency that the light has is strongly dependent on the angle that it comes out. Okay, so that was a challenge. That was what made Mr. Compton famous, and actually he got a Nobel Prize for this. He gave the explanation that I'm going to give to you now. Let me see this battery, if this is slow. Okay. And so these are my equations for the Compton effect. Okay. So if you remember well, when we studied the dynamics of relativistic particles, okay, this was the expression that I used. I used that the energy is equal to the square of the product of the momentums times the velocity of light plus there's a square missing here, okay, plus the rest mass square, the expression that you have there, okay, that's it. Okay, so essentially the Compton effect is a typical collision experiment where we have a particle. We are using the particle model now to describe the results of this experiment. So we have a photon incident on an electron, and we are going to assume that the electron is at rest in the lab. So the initial velocity of this guy is 0. And we have a very fast coming, how fast? With the velocity of light, X-ray approaching the electron, okay? What is the energy of the incoming particle is h nu. That's what we learned from Einstein. So we have this electromagnetic radiation particle that has an energy h nu that is going to collide with the electron, and at the end I will have two things. I will have one photon there and an electron going somewhere. Okay, and they will come out in the lab frame with an angle theta with respect to the angle of incidence and an angle phi with respect to an angle of incidence of the X-ray in the case of the electron. So we will have an emitted electron, an emitted photon, a new photon. So this photon is going to disappear and a new photon appears. Okay, that's the key thing. Okay, that's the story. So the initial energy of the system is simply of this system. So I should count it here. What is the initial energy? Well, is the energy of the photon plus the rest mass of the electron. That's the initial energy. Okay. What is the final energy? The final energy is the energy of the photon. This photon here now has an energy plus the energy of the electron that I have to write it in the proper relativistic way, where we write it as a product of Pc plus Me squared times C squared, C to the 4th, I'm sorry. Okay, so these are the two equations for the well, for the energy, so the energy before, the energy after, and then I have to do the same thing with momentum, the momentum before and the momentum after. The momentum before is simply the initial momentum, which is the momentum of the photon, is h nu divided by c. Where do I get this? Well, you know, look at the expression for a relativistic particle here. The energy of a relativistic particle is equal to P times C squared plus the rest mass. But what is the rest mass of the photon? The photon has no rest mass. Okay, so this term is 0 for the photon. So essentially the energy of the photon is equal to P times C. Okay, so E of the photon, E of a ultra relativistic particle, where the mass is essentially negligible, is equal to PC. Okay, but E is equal to h nu. That's what we learned from Einstein. So the momentum, the modulus of the momentum is equal to h nu divided by c, and this is what I have here: h nu divided by c times x, because this is the x direction. I didn't write it anywhere. This is x and this is y. Okay. Oh, here I have it. Okay. So everything goes in the x direction, and the final momentum, I have two contributions to the final momentum: the momentum of the photon that goes off in an angle theta, and the momentum of the electron that goes off in an angle phi. Okay. So this is it. This is all what I need to know. Okay. What is the next thing that I need to know? The next thing that I need to know is that the energy is conserved and momentum is conserved. This is a collision. Okay. So I have already chosen what the outcome of the particles are. I have the basic equation that have to be conserved. And what is my next choice is, well, you know, do the algebra for that. You know, conservation of energy is the top line. So I write the initial energy is equal to the final energy. This is equation 1. And then the conservation of momentum. I have two components of the conservation of momentum. One along the x-axis and the other along the y-axis. Yeah, it means that this projection of that momentum and this projection of this momentum added up should be equal to the initial momentum, and the other ones too should cancel out. This is what I have written there. So the first one is, this is the initial momentum, and I have here the projection in the x-axis of the momentum, and here have the cancellation. Okay. So I looked to this expression for a while, and I said, what do I want? I want to write the variables at the end in terms of the variables at the beginning, and I don't even care what happens to the electron. I'm only concerned to what happens to the photon. Okay, so the rule of thumb here is eliminate everything that has to do with the electron using the equations that you have. Okay, yeah, that's it. So how do I go about doing that? Well, there's a bunch of algebra here that you could actually follow very easily, but the thing is the following. Here you have p cosine phi and minus p cosine phi, sine phi. So what I could actually do is eliminate the angle first. How? By squaring these terms. But before doing that, I have to bring this guy to the other side and bring this guy to the other side, and then square these two guys. And that's what I've done somewhere. Where did I do that? Oh, here I have it. See, this is one side, this is the other side. What I've done here, I've taken this guy and squared it, which is equal to this term minus this term squared. Okay, and this guy also squared, so I can eliminate the angle, and I have PC squared equal to all this thing that contain the angle theta and phi. So theta is something that has to do with the photon. So I'm not going to fight with that. I'm going to keep the theta, and I'm going to keep the h nu and h nu prime in my equation, because those are the initial energy and the final energy and the angle of the photon. So that I have to keep, okay? But then again, I take this expression, the conservation of energy. What did I do here? I actually pass this term this side and square the whole thing. So I have this term square here, and this whole term here square, where the h nu has a minus sign there. Okay, perfect. Go through the whole thing. There are some things that go away. The mass, the square of the rest mass goes away, and I have all these products, and I get equation 4. Yeah, you can sort of follow it then. And then what do? I have this expression for let me see, h nu prime. Yeah, this expression 5 comes from the side of the conservation of momentum, and I have to join that expression with it says plug 6 into 4. Okay, 4 is this equation, the conservation of energy, and I said 6 into 4. I don't know where is 6. I can see 5. Ah, no, this is 6. 6 is the best part of 5, because what can I do here? That is how do I get rid? Sine square theta plus cosine square theta is equal to 1, because they are both multiplying h nu square. Okay, so this is what I write here. So h nu square is h nu plus h nu square minus the double product. Okay, now I have 6. I plug 6 into 4, and I drop many terms. You know, you can do the algebra later, but this is what you get at the end. You get h nu prime, 1 over h nu prime minus 1 over h nu is equal to 1 minus cosine theta. It's a beautiful expression. What I do next, I take out one of these h bars out, and I put one of the c's in such a way that instead of writing 1 over nu, I run c over nu. And what is this? C over nu is simply c over nu is equal to c times t. What is t? The period. But the period of the wave times c, this is equal to lambda. So that's how I get here c times nu is equal to lambda prime minus lambda equal to this expression. This is the famous Compton expression, actually. What does it say? It says, look, you're getting in with lambda, and you're getting a lambda prime that it's actually longer. It's why is it longer? Is it clear for you guys? I'm not seeing you. Okay. Let me, okay. I am here, perfect. You know, if I'm making no sense, please stop me, okay? So if you're understanding, don't worry, you know, there's more to come. But if you know, things look very odd or complicated, and this is not trivial, but there is a lot of algebra involved here that you can actually find out if it is right afterwards. Okay. Now concentrate on the result. This is what I get from applying conservation of linear momentum and conservation of energy. So essentially, what I'm saying, an X-ray comes in and an X-ray prime comes out, and this X-ray prime, which is over there, it's actually coming out of an angle theta, and depending on the value of theta is the value of the wavelength that it will have. Meaning that there's a difference between both. Yeah. Okay. So when we measured at a fixed angle theta, this is what we get. Get a graph that looks like the one here. This is not y, this is the intensity of the X-ray as a function of lambda, of the wavelength, and we get 2 peaks. And we can easily recognize that the first peak is the original is the wavelength of the original light. Lambda is this. This is the wavelength of the original light. So of the original X-ray. So why is that happening? Why do we have the original guy in there anyway? You know. And the thing is the following. Look at the expression here. The expression. How did we do this? We did this by assuming the electron is a free electron. But when I put a piece of material like this, yeah, this piece of material have electrons that are sort of flying above every other ion there, because that's a metal, it's free to move. So it's essentially a free electron. And other guys are very tightly bound to each of the nuclei there. So from the point of view from the practical point of view, those electrons that are going to be actually impacted by the X-rays anyway, independently if they are free or not, in practical terms, they have a mass that is infinity. Let's go back to the expression there. So this guy here means that this difference, the lambda prime and the lambda, will be the same if the mass of the electron is infinity. This is exactly what is going on with the very tightly bound electron. It's not that the electrons have an infinite mass, but they are not going to go anywhere because the ions are holding them together, okay, holding them very close to them. So this is almost an infinite mass electron that will see the photon coming in and will try to move, but will move with a very high mass. And when it does, it actually produces, so we have 2 types of particles in this target. We have the free electrons and the highly tight electrons, okay? The free electrons. The free electrons give rise to this thing, and the highly tight electrons give rise to that, which is very nice. Why? Because I can see directly in one graph the difference between lambda and lambda prime, plug it into this equation, make that difference, and find out if this thing actually follows the Compton rule, which it does. Okay. So this is I added 2 questions here. The first one is why I'm so sure lambda prime is longer than lambda, and I draw it directly here. Because longer wavelength means smaller energy. And I am positively sure that the scattered photon that will come out of this colliding with the electron will have less energy, because part of the energy is actually taken away by the other electron. So it makes sense that the lambda is longer, okay? Lower energy, perfect, okay? And the other question is, why can I measure also lambda at this particular angle? If this was a soup, if the target was a soup of free electrons, I will only see that peak. I will see nothing else. This is if it is a soup of free electrons, but there's no such a thing as a soup of free electrons, because if you have a soup of free electron, it will last a millisecond there, because they see, oh, we all have the same charge. They will go away and you will hit nothing, okay? So you need the material to have positive ions to keep them in place. And while doing that, some of the electrons are relatively free and the other ones are very tightly bound. Okay, so that is the explanation for this, of why the graph looks the way it does. Different subject. Creation and annihilation of particles. And I think I have a graph here. Yeah, I have a graph. This is the graph. This is the typical graph that the textbook shows. And it also has, look, in the left hand side here we have incident radiation, H nu. This H nu is very high. It's 300 MeV radiation. Okay. Has very high electrons, very high energy photons. And this is a piece of lead here. Okay. Is that right? Lead? No, I don't know if it's right. Let's write it as such. That's lead. Okay. So the radiation collides with the lead, with the metal, and then you generate particles. So you have a high energy photon that it's incident on matter, and then electrons and positrons come out. So how does this work? The process is exactly this one described here. You have an incident photon and you generate a positron, which is this guy, the red one, the red trajectory, and you generate the blue trajectory. And I'm showing them here because, you know, this is sort of this is called a bubble chamber. So there's some sort of a gas in this region here that it is bubble chamber? No, it is. I don't know the name of it. Okay, it may be a bubble chamber because when an electron goes in, it generates some sort of small bubbles that when light comes through, you can make an image of a small particle going through. And this is exactly, and the guys are taking pictures of this thing simultaneously. They are bombarding and take pictures. They don't even look at it. Okay, and this is what they get. They get this region over here has a magnetic field, okay, pointing in this direction, pointing up as such. So if it is pointing up, the electron will bend in the trajectory in that direction. And let me see, let's do this properly. And the photon, which is here, which is here, okay, will bend in the direction going down. Perfect. Okay. So we can make a pair of electron and positron. The electron and the positron are antiparticles. The electron has the same mass of the positron but have the reverse charge. So if one is plus E, the other one is minus E. So the charge is reversed. And charge is conserved here because it's also a problem. You know, there's this gamma ray, this radiation is this 300 MeV gamma ray. It doesn't have any charge on it. It's a photon, it's light, it doesn't have charge. So the outgoing thing should not have charge either. Well, you know, if you sum the charge of the electron plus the positron, it don't have charge. So the actually charge is conserved at this point. Okay. So it happens that one is negative and the other is positive, but nonetheless they are conserved. What other things should be conserved? This energy here should be enough to produce a pair of positron and let me see. I get carried away. A positron and an electron. And actually, the mass of the electron and the mass of the positron is the same, and it's approximately equal to 511 kilo electron volt divided by c squared. So this is the way. You can write this in kilogram, but it's not practical. You know, whenever you're dealing with the masses of particles in the relativistic framework, you should use the kilo electron volt, mega electron volt to describe the particle, because you know that the only difference is just multiplying by c squared, and you get the units right. Okay, because me times c squared is equal to the rest mass, the rest energy. Okay, so if you the rest energy divided by c squared, this is what I'm saying, this is the rest energy divided by c squared, that's a unit of mass, directly transformed in kilograms or grams or whatever, you know? But it's a practical way of dealing with that. So the minimal energy that if a photon or an X-ray colliding with the particle, with the nucleus here, needs to produce an electron and positron pair is simply twice the rest mass of the sum of the mass of the electron plus the positron, which is 500 kilo electron volts per c squared. Okay. So at least you need around a mega electron volt of light to actually do that. Okay. So if you have 300 mega electron volts, you're certain that you're going to produce a lot of electron hole pairs. And not only that, they will have a lot of energy. These guys, if I produce these guys, they will have almost no energy. So they cannot go in an angle. They will be actually stopped in the rest frame of the lab. You need to actually give them a lot of energy to actually have them moving, okay? So you can see them. So in practice, it's much higher than 500 kilo electron volts. It's a bit more. There's a nice technique that let me see if I can, yes. Oh, wrong screen, okay. There's a nice technique that actually uses positrons and electrons to actually get images of biological processes inside human beings mostly. So essentially you are given, if you want to do a PET, which is a positron electron tomography, the letters of the thing is PET. Okay. So this is a tomography. It means it provides a 3D images, and it's you add a radioactive isotope to a protein that binds to certain type of tissue inside the body. For example, you can add something like that resembles sugar. And we know that cancerous cells are very attractive to consume sugar, so they will be very attractive to get this thing. So you will get a high intensity or density of an image with a high intensity around a position where they are cancerous cells. Okay, and how is the light emitted? Essentially, if you have a positron, that positron gets emitted to the nearby tissue, and the nearby tissue doesn't have any positrons because only have electrons. We are built out of electrons. The positrons are actually a product of high energy decays of nucleons in general. Okay, so we have this positron, which is very foraneous. He is the only guy that has a mass equal to the electron, living in an environment surrounded by electrons. But what happens? This guy finds an electron nearby, because there are plenty of them in all the materials surrounding the position where the ion is. And what happens? They annihilate. The electron and the positron converts all this energy into into two rays of light that fly in opposite directions, essentially, okay? From the point of the collision, where it happens, the electron and the positron disappear, and two photons come out in opposite direction in order to conserve the momentum of the collision, okay? You detect both photons in synchrony in detectors that are surrounding the patient, essentially, and you can make an image of the point of the body where this thing actually came from, okay? So, and this is done so very fast, this very fast imaging process, and you can get almost instantaneous, because this is a very energetic particle also, 511 kilo electron volt. It's you know, it's a lot of energy for an X-ray. It's almost a gamma ray, essentially, and you can get a very nice. I don't know if it's very nice images, but you get reasonable quality images of some part of your body that is not very nice, actually. Okay, and then I come to the question that I'm sure has been looming on your mind, which is, okay, so I have almost 20 minutes. So if photons are good in terms of describing the photoelectric effect, we had a complete chapter at the beginning of the course that photons, meaning that waves, are good to describe the phenomena of diffraction. So, but to describe the nature of the interaction of light with matter, we need to use a model for light that is a photon. So the question then is it contradictory that if we can have a very good description of diffraction, for example, with light, you know, with using waves, the question is what happened with the particles? You know, are the particles somehow making any change here? And the answer is yes. And look what I have done, and I'm showing you here. You know, we are not familiar of doing experiments with very low intensity, because very low intensity light means actually counting photons one by one. So this is what the transparency is making here, and probably you can look at this. You can look at this section of the graph here, and you see almost nothing, because there are very tiny points somewhere, and they seem to look random. What we are doing here is the following, okay? We are doing screen, a diffraction experiment with two slits in a screen. We have a monochromatic light here, source, that produce a coherent light source here, and we know exactly what will happen here at this screen because we have calculated that in the wave model, okay? So light can go through those two places there, and you have this display of intensity graph at the end, and you can see how it evolves. It's even not clear that it's going to come out exactly as you would expect for a wave. But somehow, if you wait long enough, you can get the thing to look exactly like the wave theory of light will explain. But there is a transition here. So the question is, what is the nature of the interaction of the light with this object here, which is the slit, that we produce here a pattern that actually reproduces the diffraction pattern that we're used to, okay? So that's the question. Let's go to particles and try to describe in a reasonable way phenomena that we are so used to describe with waves so well, okay? So you're right. You know, we need new physics to actually do this kind of description in a proper way. We cannot get away with everything, you know, because what I'm saying here, come on guys, particles diffract. Well, you know, that's new physics, you know, and I'm going to give you the explanation of why. There's a principle actually that is called the principle of uncertainty that was sort of proposed by Heisenberg. Heisenberg uncertainty principle around the mid-1920s, okay? And the guy came up with this great idea, which is at the back of a new subject that we're going to be seeing in the next few classes, which is quantum mechanics, that explained that you know, if you confine a particle to a region of space, if you're saying the particle has a certain, can be in a certain region of space, in that region of space, the momentum, the range of momentum allowed for the particle to have in the same direction is actually limited. You cannot reduce that to zero, okay? So essentially what's going on is that there is some sort of new law, which is this uncertainty principle that you cannot reduce all the variables independently to zero. The position and momentum are linked, okay? So, but let's look at what goes on here. If you remember well, when we did the wave thing, this analysis with wave, this angle here, essentially what we did was look at a certain angle in that direction, see, and the difference, if this guy is here is, no, I'm sorry, if this guy is here, theta 0, the difference in path here between this guy and this guy should be equal to 2 pi in order for these two guys to arrive at this point, completely producing a completely closed loop, okay? So remember we did this thing, you know, and we got this circle of things. So when the contribution from this side and the contribution with that side are in phase, in the case of diffraction, what you get is a minimum contribution at this point, okay? How is that? That simply means that theta naught is equal to lambda over A. That is exactly the value of theta naught when that happens. So then I repeat the question, how do we explain that a photon with only vertical momentum, this is the photon initially has a momentum only going in, oops, no, okay, oh, there you go. Only going in that direction, in the vertical, in the y direction. When the photon goes only in the y direction, how the hell does it get enough momentum to get there? Because to get there, it means that it has to go in this direction. So this is a particle that actually has to go in that direction. So this is where the new physics come in, and we have this uncertainty principle. So we need new physics to go beyond Newton. Yeah, we are gonna use two concepts here. One is the concept of probability of occurrence of a certain event. For example, we can think of the particles. You know, if we look at these images here, we can see that you know they start to pile up where they should be. So one goes here, one goes here, but they go very close to the center here with the maximum probability. So they are closer to this axis with more probability than to any other place in the screen. So we're going to say that the photons has a higher probability to be in this thing. It's consistent with the experiment. And the probability and you can see there's no certain location where the photons will be. So it will arrive here with a certain probability there. And when you add up all of them, you get the yellow curve. Okay, so more probability along the central direction, and slower probability everywhere else. And in a certain region, this goes to 0. Okay, so the probability of receiving any particles in that direction is close to nothing. Okay, there's a line there that has no intensity of photons whatsoever. So I mean, right there. I'm sorry, I point with the pencil. I forget that you don't see that. Okay, in those lines, if you follow that line precisely, you know, but there are some scattered points, each one around them. So the thing is not deterministic anymore in the case of the particles that comes out of the of the second slit. Okay, so there's the concept of probability, and there's this uncertainty principle that I would mention. So this is the new thing. Okay, this is the new thing. We can now associate a wave to a particle as, you know, the wave that represents a photon, and the waves associated to the particles somehow represent an amplitude of probability. That's what it is. Okay, so whenever you want to find out what the probability of finding a particle in a certain position, you take the wave function, that wave, and square, and that will be the probability density. You actually have to multiply by a certain volume here, delta volume, okay, to get to know where the particle is. So this phi x squared is a probability. If you multiply, essentially the volume is larger, the probability is larger to finding the particle there. Okay, so this is the first aspect which is different, and the second has to do with this uncertainty principle. So, and I'm going to try to convince you that the uncertainty principle is actually what provides the basis to describe the diffraction experiment good for the particle. Look what this curve here shows, the intensity as a function of angle. This we calculate with this thing here. We calculated with wave theory, but in this model that now we're using photons, particles, this essentially is sort of a probability. This means that there is a, that there's a higher probability in this position than in this position to receive a photon. And then the photons will start hitting this thing randomly in different places, but essentially you will end up building more photons in this place than in this place. Okay. For the moment, I'm going to forget of everything that goes beyond theta 0. I'm going to erase those things out and say, you know, this is almost 85 to 90% of the photons hit in this place, but I would say it's a whole of it, just for the sake of argument. And I'm going to claim also that what I'm interested in describing is why this thing actually arrives to 0 here. Okay. And this explanation is given in a reverse way. It's not that it arrives to here. This is the maximum value that it can have, considering considering that we are confining the electron, I'm sorry, the photons to be in this position in range in X. So the principle of the uncertainty principle, the Heisenberg uncertainty principle related to momentum and position is expressed in this way. Delta Px, which is the momentum in this direction, in the X direction, times the variation of the position. This is simply, you can understand delta Px is as something like the range of momentum, and this is the range of position. And the range of position here, roughly, is the size of the slit that the photons has to go through. So before the light arrives to the slit, here, when you have a wavefront, actually the wavefront has the same amplitude everywhere. So it's completely delocalized particle, because also a wave has a single wave. If it is a single energy or a single wavelength, if it has a single wavelength, remember the wavelength in the model of Einstein is associated with the energy. A single wavelength means a single energy, okay? A single energy means a single momentum in the case of the photon. Okay. Oh, we have a single momentum. If we have a single momentum, it means delta px is equal to 0. No px here. If delta px is equal to 0, delta x is equal to infinity. Okay, so if it is completely defined, the momentum in this direction, it could be the photon could be actually anywhere in this horizontal plane that I'm showing here. Okay, and this is exactly true. This is this explanation. But as soon as it's arrived to the slit, you are forced with a certain value of delta x. How much does delta x cost? Well, delta x is roughly equal to a. Now, if delta x is equal to a, it means that you will add a delta px. If you change delta px, it means that you have to change the wavelength of the light. Okay. Okay. So now I'm trying to find delta px. I'm going to change the color of this thing. If I'm trying to change the color I'm trying to change the momentum, delta px, I'm sorry. Delta px, if you look at the graph, I'm doing this graphically, okay? The delta px, if this is p, the incident momentum p, and this is px, okay? The incident momentum is almost, this side is almost equal to this because the angle here is very small. So delta px is equal to py, essentially the momentum along this direction, which is equal to that one times sine theta. For that angle would be sine theta naught. So that will be py times sine theta naught. I could, since the angle is small, I could write it up as, can I get rid of this? No. Oh no. How do I erase that? This is okay. So py is times theta naught. This is equal to delta px. So delta px, the magnitude of the momentum in the x direction for theta equals theta naught is essentially the momentum on py, this one, times theta naught. That's an approximation. So this should read actually like an approximation. Okay, should read something like that. So I replace everything here. So h nu divided by c, this is momentum in the y direction. Sine theta is equal to theta times, what is this? Times a. What is a? Where does the a come from? This here is what is my argument here? Okay, here's the argument. So this is the delta px, and this is the delta x. If I multiply everything together, what do I get? Something of the order h. So for my particular experiment here, the one that I'm using, that I'm seeing with this slit of size A, if I multiply delta px obtained from the graph by the size of delta x, which is equal to A, I get something of the order of h. What does the principle of uncertainty says? It should be a little bit more than h bar over 2. So it should be greater than h bar over 2. Well, this is greater than h bar over 2, but it is of the same order. So what I'm saying here now is that this graph, this intensity graph that goes like that, new pen. This graph here. No, what happened now? Okay. That graph over there can be explained in terms of the uncertainty principle. Okay? Because it is consistent with this view. So it means we don't have to be very concerned of actually thinking that the radiation or the light are photons, so they are not going to diffract. They do diffract because there's another principle that makes them diffract, which is this uncertainty principle in the momentum. Okay, and we are going to get something very close to the graph that we're getting by the same model. Okay, I don't think I have. Yeah, I don't think this is going to add to the subject. Okay. Okay, so this is it for the day. And I have nothing else to add. I don't know if you guys have any questions.
Actually, I have a question relating to one of the homeworks.
Okay.
Yesterday I was actually doing I think it was the homework given on the lecture number 11.
Okay.
Which was the Santa Maria radio.
Okay.
Emits a certain power, and I was trying to actually determine it. It was particularly difficult trying to understand how I should work when I only know, for example, the power of the that it is emitting. I think I understood that one had to actually get the actual radio frequency that is the Santa Maria radio. I think it's 102.3 megahertz, if I'm not wrong.
99.7.
But trying to get, for example, the photon density,
mm-hmm.
I just really wasn't able to. With all of the details we had available, I really just wasn't able to know how
you really need the frequency. Okay. Then
I was able to actually get the frequency, and I was able to get the intensity. But when I tried to like take it out, because I know that the formula was intensity equals to photon density times velocity of light times what would be the energy of the photon. And it would be that the photon density would have a magnitude of 1 over meter cubed. And I thought that just doesn't seem right.
Well, the thing is, if the density is exactly 1 over meter cubed.
Oh, okay. Oh wow. I doubted myself when I had the answer. Hold on.
Yeah, because it's a density. A density is simply a number divided by the volume.
I was like, then I should be able to send it today. I wasn't able to send it yesterday.
No, that's okay. It's okay. Yeah.
All right. Thank you for that.
Yeah, that was easy. But, I can. Yeah. Yeah, work out and send it whenever you can. Yeah, it's better than that you think about the subject here and not. These are always things that are confusing, okay? Because there are many radial dependence. The intensity decays with the distance, okay? That's why the 1 kilometer is relevant. But the power, the intensity decays with the distance, so the density decays with the distance. That means that the number of photons that you actually find out at a certain distance it's lower, simply because if you're closer, the same number of photons are in a reduced volume, okay? And then when you start increasing the surface of what you're looking at, and you have a uniform distribution, whatever you decide is uniform, then the thing actually has to decay. The density has to decay. But the density is indeed 1 over meters cubed. Okay, that's the actual value of density. Okay. Okay, guys, next class, we're gonna have a practice online homework, meaning we're gonna solve a small problem. We're gonna do a homework during class, okay, just to find out how do we work this thing of the exam, okay? So please try to have access to camera. I would like to see you guys doing this mock exam or mock homework. And also would like to that you have the resources to actually submit it to me after you have done it. Meaning you must have the ability to actually scan the thing and send it to my email. Okay. Okay, guys. So we meet next Thursday, and I am sure I'm going to be a bit late because with the other class I have an exam. Okay, so these guys are going to give me a hard time, and they're not going to let me go out as fast as you guys would need. So I may be a few minutes late, but don't go away because I'll be there. Okay. Okay, so let me see if I could. Where's the recording? Stop post recording.